Today, we are presenting the first video compression scheme that gets better as you use it, OVAL, Online Video Compression Using Autoencoder Learning. Real-time video conferencing has become increasingly important due to the COVID-19 pandemic. Video data needs to be compressed during transmission, and we seek to develop a new compression system using online learning. Online learning is about continually training on data which becomes available after model deployment, such as frames in a video conference. OVAL uses this to train an autoencoder that compresses in latent space and improves on these compressions in real time. The compressed data is then transmitted and decompressed at the receiver. The inspiration behind this model is the static nature of sitting in front of a computer camera. The video will be mostly static, hence it will be easy to learn. By training in real time, we can achieve better performance. Here's a high-level diagram of the OVAL system. Input frames come from the sender and are encoded, transmitted, and decoded in the critical path. This initial encoder is pre-trained from an offline model. Separate pipelines are used for training better quality representations. Then, we compare the live and train error, and if it meets a certain threshold, we update the live autoencoder. This allows for concurrent learning with encoding in real time. When a video starts, OVAL uses a pre-trained autoencoder. We need to create our own dataset since there are no open source video conferencing datasets available. So, we selected videos from YouTube using the following criteria. The video had to focus on a singular small set of speakers in front of static backgrounds. Videos were 2 to 5 minutes so they could be preloaded into RAM for faster training. And the videos had to be in different resolutions for more resilient training. Here are some examples of the speakers we used. We also had to ensure diversity since our data focuses on human faces and expressions. As you can see in the figures, diversity was ensured across gender, race, and language.
In terms of data processing, we use two different pipelines, one for offline and one for online. For offline, we added Gaussian noise to all the frames. And what this does is that it prevents overfitting because in the batch sizes that we used, it was within a second. So all the frames are similar. And then what it also does is that it enforces the model to learn useful features. And in terms of online training, we have to make sure that the data keeps up with the now current frames. So since it takes time to process all the information, we are only loading every 2 or 2.5 frames. Moving on to this side, we can see the Gaussian noise in our frames, and we can see that the model must learn important features to be able to recreate the image correctly. Our model itself was a 5-layer convolutional autoencoder with the encoder and decoder segments being symmetrical. As you can see in the diagram, as the depth increases, we get smaller heights and widths and more channels, which ultimately results in a 23.5 times compression ratio. We tried to use deeper models, and we also tried to use LSTMs and conv LSTMs, but ultimately due to time constraints and loading and the fact that this has to work live, we decided not to go down that route. Moving on to the pre-training, if you look at our loss function, which uses BCE loss, which is the industry standard, we see that the loss is plateauing and there's no evidence of overfitting. And if we compare this a BCE loss to MSE and MAE loss, which we didn't train using, we can see that it also follows a similar pattern, which shows that our model isn't just gaming the BCE loss function, but is learning important features.
While offline pre-training gave strong results, the true novelty of OVAL is the online learning component. When the OVAL model was applied to new test videos that were not seen before in pre-training, online learning was able to achieve a reduction in loss of up to 75% compared to just using the pre-trained model. For this example video shown here, we see that the offline model stays very consistent at the same video quality throughout the video, whereas the online model consistently learns features throughout the video which decrease the loss, therefore improving the video quality. This is a key result since online learning with online compression has actually never been implemented before. We can verify our quantitative results looking at actual video frames from our test videos. We see that early in the video, around 5 seconds, the image is blurry with poor color saturation, but by 60 seconds, our online learning model has picked up on features, the image is not blurry anymore, and the color saturation is proper to the actual video. Comparing to our benchmarks, we see that OVAL with online learning, achieving a 23 times compression ratio, produces a clear image reflective of the actual video being transmitted, and without online learning, the image is blurry and the color saturation is not as good. Then, using simply bit dropping, so dropping the least significant bits, we have a very bad image quality at only 4 times compression. And using image interpolation, which resizes the image and then sizes it back up using interpolation techniques, we have a 20 times compression ratio, but a terrible quality image. Once again, showing how Oval outperforms both benchmarks and using the model without online learning.
Here we see two different deployments of Oval. On the top, we have a video that was relatively static, just someone sitting in front of a camera and talking. In this case, Oval was able to quickly memorize their background and was able to get a 75% improvement in the real-time received error within a few minutes. On the other hand, we have a second video where the speaker keeps changing every few seconds, and Oval had a much harder time learning that because the background keeps changing. However, it was still able to get a 25% improvement on its loss. Believe it or not, you've actually been watching Oval this entire time. As you can see in the bottom corner of my screen, this is just a window that the program is generating, and it's being decoded in real time. This is running on a 3-year-old machine with no GPU that was entry level, and yet it is able to run Oval with absolutely no problems. You can see here that within the course of 3 minutes on just the CPU training, we were able to half the loss that we got after 18 hours of GPU training. That is how powerful the online learning of Oval is. You can see here that we can keep the live error as compared to the training model as small as we want by just broadcasting an update whenever our trained model gets sufficiently better than our live model. This is keeping at our 23 compression ratio and at the real-time constraints of 15 frames per second, which is the target that we had set. It's able to do that despite running an iteration of approximately 10 frames only every 3 seconds. And we can do this because that's done in a different thread training on a buffer of the most recent frames. By applying online learning to video compression, we were able to design the first real-time video compression algorithm that gets better as you're using it. In the demo, we showed you that it can achieve high frame rates and achieve high-quality compression, all while making significant improvements in a very short period of time. It works particularly well for Zoom-style videos and could be very helpful for video conferencing.